Hey YouTube, I'm Sergeant Indy. Welcome back to my turn-based strategy tutorial for GameMaker Studio. This video, we're going to be coding a function that'll show the selected actor's movement range and all of the little fiddly bits related to that. Word of warning, this video is going to be a bit of a slog. Normally I like to code a little bit, then run the game, then back to coding, back and forth, and I like it that we can sort of take breaks to see our incremental progress, but this video is just going to be coding from start to finish before we can finally see it all run at the end. So, here goes. First up, we've got a few variables we're going to need to throw into our node object and our actor object. We're going to do the node first. So head into our node's create event, and somewhere top-ish, we're going to do color equals C_white. Later on, we're going to use it, well, later on, in just a little bit, we're going to use this variable to allow this node to draw its sprite a different color. We're going to be giving all of our units two actions, right? And they can use either or both of those actions for movement. So nodes within the range of a single action's worth of movement will be blue, and nodes within the range of 2 actions worth of movement will be yellow, as well as any movement that would essentially end a character's turn. So if you've already acted, all of your movement is yellow because that's the end of your turn. Default, white, of course. So then down at the bottom-ish, right above cost, we're going to do a new thing. We're going to do pathfinding variables, and I like to give them a little tail. Whoa, not you. I'll give them a tail like that, so that when I'm scrolling quickly through a bunch of code, and I don't think this is going to get too in-depth, but it's good practice. Makes it easier for me to find what categories each variables belong to when I'm looking for something specific. So, cost is obviously related to pathfinding. That's how much it costs to move through this node. And that's important when you're trying to figure out how far you can move, obviously. So we're going to add some more pathfinding variables, though. And the first one up on the chopping block is parent equals no one. So parent is another requirement for pathfinding. It's going to hold on to the ID of the node that scores it. Later on, we'll use this to make an actual path for our characters to move along to follow. When we click our destination node, we'll be able to get its parent, and then that node's parent, and then that node's parent, and so on and so forth until we reach the source node. So following this line of parents back to the origin is how we build our pathing. It's pretty cool. Next up, G equals 0. So the G score represents how far away this node is from the source node. That's, again, where our actor is standing. Finally, one more variable, move node equals false. All of the squares that we give a G-score to will also enable this move node variable. It's just an easy variable test to determine whether the player is clicking on a valid square for movement or not. And that's all we need for this create event, but we need to add ourselves a draw event. We just did this color variable, we need to utilize it. So let's green check out of here, add event, draw. Mute my computer real quick. I don't want to catch any like instant messages or something. That would be really obnoxious. No more events. Okay, so draw event, drag in a block of code, and in here we're going to do draw sprite extended. Now, before we were just doing, well, actually, have we done a draw sprite extended yet? I don't even remember. I'm going to talk about it briefly then. So if you'll see down here, this expects just a whole mess of arguments to it, but these are all arguments just sort of pertaining to drawing sprites in general. And a lot of it is stuff that sprites just kind of have. So the sprite we're drawing is our own sprite index. That's essentially, when we set it to S node, that's what that is. The sum image is going to be -1, which means I want it to animate. Now I know it's only got one image in there, but it's good practice. And if it did have more images, maybe it had some grass that would kind of wiggle in the wind or something, it would animate if you did it like that. Our x, we want to be the object's own x. Our y, its own y. X scale of 1, y scale of 1, rotation of 0. We don't want it spinning around on us. For the color, we'll set it to that color variable we just did. And its alpha, we'll set that to 1. All done. So, all this is going to do, like I said, is if we assign it a color, like yellow, then it will draw the sprite yellow instead of its default appearance. Also, when you see it draw that color, that's the same thing as if you had done like a draw set color C_yellow. and forgot to switch back to white afterwards, every sprite would be drawn with this tinge of yellow. It's kind of a mess. So you'll see why that's a bad idea, because you'll see what yellow or blue sprites look like. You wouldn't want your whole thing looking like that. Okay, so we're done with the node object for today. That's it. I've talked about it way too much. It really isn't that complicated. Green check out of here and there, and we're going to go into our actor, and we're going to add a couple more variables right after the name. Do character statistics. And in here, we're going to do move equals 5 and actions equals 2. So, like I said, we have 5 squares of movement, and we have 2 actions. So if we want to spend both actions on movement, our actors will be able to move a total of 10 squares. That's all our parent actor will need for today, but each of our characters, Danny and Sandy, they'll need a little bit of love, and I'll explain why in just a second. Let's green check out of here, all the way out. Let's go into Sandy. Now, Sandy is a child of actor. We've got actor set as our parent. That means that Sandy will inherit and do anything that the actor does, unless we override it. So, we have our own create event. So Sandy's not actually doing the actor's create event anymore. That's a problem, because that means that Sandy, well, she gets a grid X and grid Y when she's created. That's not a big deal. But the problem is that Sandy doesn't have access to move or actions. So we need to fix that. So how do we fix that? Well, event inherited. And I always wait for this one to go out because I've inherited. It's one of those words my brain and my fingers disconnect, and I can never type the stupid thing right. So these are each children for our parent object. And if we type this event inherited thing, they'll do the actor's create event. And then they'll do whatever we have after that. So in this case, our actor is going, all right, grid X equals 0, grid Y equals 0, name equals air, move 5, actions 2. And then Sandy goes, oh, wait, actually, my name is Sandy. And then we've got both events done. Easy. Green check out of there, and we got to go into Danny and do the same thing. So, event inherited. There we go. Now, Danny will do the same thing. Easy. Green check out of here. Now, we've got a series of scripts to make, and they're going to be our first batch of scripts for this entire project. We're going to do the small ones first. We're going to just call it a warm-up for the great big whammy that's coming our way. Let's open up a new script, and we're going to call it wipe nodes. So double-click up here, wipe _ nodes. Now, this script doesn't need any arguments passed to it, so we don't got to do that. We can just call it with just like wipe nodes, open close paren. That's it. But all this is going to do is reset data of all nodes. And it's essentially going to give every node in the room a factory reset. We're going to do that with a with statement. So with onode. And again, this is a very powerful piece of code because this will take every single node in the room and have them run the code between these two squigglies right here. So move node equals false. G equals 0. Parent equals no one. Color equals C _ white. Okay, so this guy's going to be called a lot because essentially whenever the pathfinding script runs, it's going to fill the nodes with data. And then when we're done with that data, we're going to run wipe nodes to clear all that data out. Now, you could just do something kind of silly like call movement range, well, call the one that fills the data in the nodes every single step, and then just wipe it at the beginning of every step so that when you don't need it, it'll be wiped. And I've done that. My first prototype, I called it every single step, and then I wiped the nodes at the begin step, and then I called the movement range if it was necessary at the middle step to overwrite the wiped nodes. It was messy. It was kind of gross. It's not nearly as much of a performance hog as you'd think it'd be, but it's a strain on on the system, and it's terrible practice. There's a lot of data being passed around in a turn-based strategy game. We've got to make sure that we're handling it in a controlled, deliberate, somewhat responsible manner. So when we call scripts that fiddle with the nodes, those nodes are going to stay messed with until this script wipes them. So let's close this one out. We're going to do another small script. So let's get out of here. Another script. We're going to call this one color move nodes. Okay, now this is going to have 3 arguments passed to it. First one, argument 0, because it starts count at 0, is going to be the node ID to color. Color, there you go. Argument 1 is going to be selected actors move statistic, and then argument 2 is going to be the selected actors actions. Okay, so let's take and make 3 variables. Var node move actions, and then node equals argument 0, move equals argument 1, actions, guess you guys know where this is going, equals argument 2. Okay, so if actions is greater than 1, so if we have our, factory default 2 actions, then we've want to color some of these nodes blue and some of these nodes yellow. So if node.g, and remember that g scores how far away a node is from the origin node. So if that is greater than our baseline move statistic, then its color is going to be yellow. So node.color equals C underscore yellow. Else, so if it's within a single action's worth of movement, we're going to color it blue. Well, not blue. Blue's too bold. We're going to color it aqua, so it's soft and it matches the yellow a bit better. So node.color equals C underscore aqua. There we go. Now, if we don't have 2 actions, if we've only got 1 action, or hypothetically 0 actions, though if we have 0 actions, this isn't ever going to run. But if we only have 1 action, else node.color equals C underscore yellow. Again, the pattern we're going for here, and people are good at picking up on patterns. It's what makes games fun, and it's what makes people good at games. It makes humans good at doing human things. So the pattern we're going for is if a movement would end your turn, those squares are yellow. So if it's your last action, any movement will end your turn. And if you've got both actions, then far movement will use up both of your actions. It'll end your turn. That's the pattern we're going for. And you should always strive for some sort of simple pattern that's easy for people to pick up while designing your games. Because, again, picking up these kind of patterns, it's fun and it's intuitive. We do it without even really thinking about it. So that's good game design, fundamental. And I've rambled too much about it. That's basic stuff. Okay, so anyway, pretty easy. We're going to pass a node here, and we're going to pass our actor's move and its actions, and we're just going to change the node's colors. Done. No problem. You may be worried, like, hey, there's nothing for white. Well, the white nodes aren't going to be passed to here. The ones way out of range aren't going to be passed to here, and to get them back to white, that's what white nodes is for. So hopefully you're kind of getting how all of this fits together so far. And now it's time for the big one. We're going to create a new script, and this is that big pathfinding script I talked about in our last video, which a lot of people seem to skip, but this is the one that's going to calculate our movement range, and it's going to get all the nodes on board ready for movement. So we're going to call this movement range, because, I mean, it's not very creative. When it comes to naming scripts and stuff, you shouldn't be creative. You should be straight to the point, because you got to remember this stuff a month from now when you're still working on the same game. So argument 0 equals the origin node, the node to pathfind from. Argument 1 is going to be the unit's movement range. Argument 2 is the unit's remaining actions. Pretty simple. Now, I've hemmed and hawed about how I'm going to do this, how I'm going to get this whole big block of pretty complicated, weird code out to you guys. It's a mess. So what I've decided to do is I've just got a good set of comments lined up before every snippet of code, and I'll just kind of explain as I go, because it seems to be the most quick and efficient way to just beat our heads against the wall and get through this. So, everybody ready? Here we go. The first thing we're going to do when we call movement range is to reset all node data, all of their data. We don't want any of these nodes coming into this having a leftover G-score because something didn't declare right, or maybe they're already colored something silly. We don't want anything like that. So, the first thing we're going to do is wipe nodes. Boop, done. Now let's do some variables. Declare them. Var, open, closed, variable, start, current, neighbor, variable, temp G, range, cost mod. Done. Okay. So, and I've kind of done these in an order. These two are going to be our data structures. These three are going to be our main working variables, the ones that were like the top level variables, I guess. And these are the ones that we're kind of fiddling with. These, actually, I take it back. These are going to hold on to instance IDs. That's a much better way of putting it. And these are the variables aside from that. Okay, so declare relevant variables from arguments. Obviously, we pass these arguments in here. We intend to use them. So start is going to equal to argument 1 or argument 0, the first argument. Argument. Oh my god. Argument 0. Oh my god. Argument 0. It's a little earlier than I normally... Well, no, it's not even. It's noon. Maybe I'm just hungry. At any rate, I'm having issues. Already this is like my 4th take. It's just been terrible today. Okay. Start equals argument 0. Range equals argument 1 times argument 2. Okay. Done. Obviously, this is the node we're starting from, and this is the current number of nodes out we're going for, because I can't move further than that. There's no point in doing nodes past that. Create data structures. So open equals ds priority create bloop. Closed equals ds list create. Now, we've fiddled with lists before. We know they just kind of hold data. Pretty easy. A priority list, priority queue, priority thing, whatever it's called, right? What that does is it's kind of like a list, but every time you put something in there, you put it in there with a numerical value attached to it, and that's its priority. And then it will sort of sort things in the list in accordance to its priority, and you can do things based on that. In our case, we're going to put instance IDs of nodes into our priority queue, and we're going to put it in there with a priority equal to its G-score, and then we're going to grab the lowest one and do stuff with it, and we're going to keep going until there's nothing left. All right. Add starting node to the open list. So ds priority add open start G. As I mentioned earlier, this is how you add things to a priority list. Yeah. So that's the list we're adding to, this open queue, open priority. I think it's a priority list. Maybe it's a priority queue. Nomenclature's throwing me off, but it's not that big a deal. This is what we're adding to. This is what we're adding to it, the instance ID of our start node. And we're adding to it with a priority of its G, which we just set to 0 with wipe nodes. So that'll definitely be the lowest one on the list, despite the fact that's also the only thing in the list. At any rate, we'll add more later. So, while open queue is not empty, repeat the following until all nodes have been looked at. So, while ds priority size open is greater than 0, we're going to do a lot of code. Now, you have to be really careful with these while loops, right? A while loop will run until this happens. Period. Forever. So, if you're not careful, it's very easy to get yourself locked into an infinite loop where you have to like Control-Alt-Delete and kill the game that way. We don't want that to happen. And it won't happen here. I'm just saying, be careful that you are sure your exit clause can happen, because otherwise it's going to lock up. So, and you know, that happens to everybody. Certainly happened to me a lot doing, I think, my 16th video. It's pretty brutal. I had just a real killer of an infinite loop and I couldn't figure it out. I probably Control-Alt-Deleted that thing a dozen times. So don't stress out too much if it does happen to you. It happens to everybody. Just try to get to the bottom of it. So, the first thing we're going to do is remove node with the lowest G-score from open. So, current equals, and that's current, that's whoever we're currently working with, is DS priority size open. No, priority delete. I got so mixed up. Delete min open. I definitely need food. All right, so we're removing whatever has the lowest priority in open and stuffing its ID into current. Now we need to add that same node to the closed list. The closed list, I've seen another naming scheme for this, is that some people call open frontier, as in this is undiscovered. This is where we're still looking out. And visited. And when a node is visited, that means, oh, we've been here. We've looked at this. So that's essentially what the closed list is. So ds list add closed current. Okay. And I should probably comment that too. So add that node to the closed list. All right. The point of the closed list is we're trying to make sure not to go back there again. So now we're going to step through all of current's neighbors. So we're going to do this with a for loop again. For I equals 0, I less than ds list size neighbors, I plus equals 1. Great. Open squiggly, close squiggly. Going to do all this mess. I should give myself some breathing room. Let's do that now. Whoop. Okay. If you're falling behind, go ahead and pause it now and make sure you're up to this point, because I'm about to start working in here. All right. So in this mess of a for loop, what we're going to do is store current neighbor in neighbor variable. And that's kind of confusing because it's current neighbor. Yeah, okay, well, whatever. So neighbor equals ds list find value current dot neighbors II. So that'll be whichever neighbor we're currently working with. And now we've got a bunch of things to do. We got to add neighbor to open list if it qualifies. What qualifies, you ask? Neighbor is passable, so it's not a wall. We don't want to add a wall to this list. We don't want to do anything with walls. Walls aren't a part of pathfinding. They're an obstacle to be avoided in pathfinding. Neighbor has no occupant. We don't want to go moving through someone else's space. That's their space. We want to go around them. Neighbor's projected G-score is less than a movement range. So if this square would be outside of where our characters are the furthest possible they can move in one turn, we don't want them on the list. Get rid of them. Who cares? And then finally, if the neighbor isn't already on the closed list. And that's what really cuts down on this silly thing right here, is the closed list. Because our neighbor has 8 neighbors all the way around it. And all of those neighbors, so current has 8 neighbors. And all of those neighbors have current as their own neighbor. So that's why adding things to the closed list is important, because otherwise we'd just be fiddling through all these guys' neighbors, and eventually it would get done. It would just take much, much, much longer than it has to. And we don't want to do that. We want better coding practices than that. So we're going to check for all of this in one big fat ugly if statement. Let's do that now. If ds list find index closed neighbor is less than 0. Okay, let's talk about that. DS list find index will return 1 or -1. And essentially it's like, hey, do I have this neighbor in the closed list? And if the answer is no, it'll return -1. If the answer is yes, it'll return 1. So we're checking if it's not on that list. So if it's not on the list and it's passable, so neighbor.passable, and it has no occupant, so neighbor.occupant equals no one, and finally, and neighbor.cost plus current.g less than equal to range. Great. All right, so if all of that is true, we can add it to the open list. We got to do some other stuff first. We got to score the node. So only calculate a new G-score for neighbor if it hasn't already been calculated. So if DS priority find priority open neighbor equals 0. So if it's somehow in the open list but has a G-score of 0, then it got on the list somehow without being scored. Or DS priority find priority open neighbor equals undefined. Now, undefined is another keyword, right? In this case, if DS priority find priority, right? If it doesn't find neighbor, it'll return undefined. I think it'll also return -1, and I just ruined it with a bad click. Let's just Control Z that. That was a mess. Okay. So yeah, if it's somehow already on the list, but still has a score of 0, well then it hasn't been scored, has it? We need to do something with it. And also, if it's just not on the open list at all, then we're going to do this stuff in here. So, first thing we're going to do is cost mod equals 1. We're going to make it so that diagonal squares cost 1.5 times whatever the cost normally is. So it's more taxing to go through diagonal squares. This is a throwback to D&D where essentially every other square of diagonal movement costs you 2 squares of movement. So if you go 2 squares diagonal, that's 3 squares of movement. Anyway, we're going to do that. So, we also need to, before we get into that, we need to give neighbor the appropriate parent. So, neighbor.parent equals current. So, easy. We're scoring that node. We're getting to that node from current, so current is that node's neighbor. If node is diagonal, create appropriate cost mod. So, if neighbor.gridX doesn't equal current.gridX and neighbor.gridY doesn't equal current.gridY. My brain just completely lapsed out. I'm going to have some delicious macaroni and cheese in a bit. Cost mod equals 1.5. Maybe that will get my blood sugar up or something. And I'm really out of it. I don't know why I spaced out. So the easiest way to check if something is diagonal is that its grid X and grid Y will both be different than what the current node is. Because if it's just left, well, then we've just got the same grid Y, right? And if it's up, we got the same grid X. But if it's diagonal, well, we don't have grid X or grid Y, and it doesn't matter what direction you go, it will be different. So that's the easiest way to check diagonals in a grid-based game. Finally, calculate G-score of neighbor with cost mod in place. So neighbor.g equals current.g plus parentheses neighbor.cost times cost mod. So if it's a diagonal, it'll cost a little more, and if it's not, then we just add the normal cost. But that's how we get the neighbor's G-score. Great. Now finally, we need to add neighbor to the open list so it can be checked out and be check out to exclamation point. Okay, ds priority add open neighbor neighbor.g. So if you'll notice this open neighbor.g, it's pretty similar to our open start.g. We're just throwing them in the priority list with a priority equal to their g score, and then essentially first come first serve, we'll delete the lowest and we'll do all of this stuff with them, and we'll keep going till the open list is completely empty. Now, we're not quite done here. We need an else. We need a big, fat, gross else. So, right here, after this ds priority, find priority, on this line here thing, right after this, we want the parentheses to match up, the squiggly bits to match up like that. We're going to put an else. Open, close. And I'm going to put the comments for the else above the else, because that seems like an important place to put it. So else, exclamation point, if neighbor's score has already been calculated for the open list, we're going to recalculate it if it fits. So first thing we're going to do is figure out if the neighbor's score would be lower if found from the current node. So say like we had a node go out like, oh, up and then left. Oh, okay, well that's 2 movements, but that's still diagonal to where we started. It would be only 1.5 to get there from him. So that's why we're doing this sort of brief recalculation, like, hey, can you get here better from another node? Okay, well then get there from that node. Easy. Just sort of optimizes all of our movement and paths. It's important. Okay. So, first thing we need to do is obviously cost mod. We need to do that again. Cost mod equals 1. And then if, in fact, you know what, to heck with it. Let's just copy all of this, Control C, and let's Control V it down here. So, if neighbor grid X is yada yada yada, our cost mod is 1.5. And then temp G equals current.g plus neighbor.cost times cost mod. Okay, so figure out neighbor score would be lower from the lower current node, and then if so, okay, so check if G score would be lower if temp G is less than neighbor.g. Bloop. Let's scroll down a bit. Get it right here. Then neighbor.parent equals current. Neighbor.g equals temp G. DS priority. Change priority. Open neighbor G. .g. Very important. So, if, like I said, if the G score would be lower, if the movement cost would be lower from the current node than from the last node that scored it, we're just going to change its score. Easy. And we should have 1, 2, 3, 4, 5 squigglies. 1, 2, 3, 4, 5 squigglies. Let's line all these guys up nice and neat. Now I like to leave a space between them in case I need to come back and add more code later. Makes it easier to just dive right in. And one less thing to do to keep me from losing my train of thought. Don't worry, when I'm completely done with the script, I will kind of scroll down it slow and you can pause it and try to catch up if you're falling behind. So, we're going to round down all G scores for movement calculations. This is me being a nice dungeon master, right? If that 1.5, well, it could either be 1 or 2. How's it going to be? I say if it's 1.5, go ahead and round it down. Go ahead and have that square. I mean, because if you can only move 5 and that square costs 5.5, let them have it. That's what I say. So with onode, G equals floor G. So that will cut off any sorts of decimal place. All of them are gone. Easy. Now, like I talked about earlier, just very briefly, we have 2 data structures. What data structures do is they allocate a big bunch of memory for that data structure. When you're done with a data structure, you need to destroy it. If you don't, then every time this runs, it's going to allocate a new block of memory for open. Then it'll run again, and a new block of memory for open. Next thing you know, you're leaking like 20 megabytes a second. You don't know what's going wrong. You're freaking out, and it's because you didn't handle your data structures properly. Trust me, I've been there. I've had a massive leak on a very simplistic game. Drove me nuts, and it was because some stupid list wasn't getting destroyed proper. So, you create a list, destroy a list. So, DS, priority, destroy, open. That's it. So, destroy, open, super important. No leaks, exclamation points. No leaks ever, guys, right? We're going to get them all. Got to plug them all. So, now we need to color our move nodes. Let's color all those move nodes. Then destroy capitals. Destroy. Then destroy the closed list as well. So, easy thing to do is that we have this list. It's got every single node on that list. So, for II equals 0, II less than DS, list, size, closed, II plus equals 1. Bloop, get out of there. Okay. Current equals DS, list, find, value, closed, II, and then current dot move node equals true, and color move node, there we go. Current, argument 1, argument 2. Why is this freaking out on me? Color move node. Oh, I named it color move nodes, plural. Fine, color move nodes. Although really, no. We're going to go back and we're going to change the script name. It only colors one at a time. It should be color move node. Just, nomenclature is important. So, destroy, closed list. Exclamation points. Super important, guys. DS, list, destroy, closed. And I mean guys or gals. I grew up in California in the 90s, so dude and guys are like gender neutral to me, and I apologize if that offends anybody, but I don't know, like I said, I'm used to those being gender inclusive terms down where I grew up and when I grew up. So green check out of here, and we're going to go into color move nodes, and we're going to change it to color move node. Okay, there. Get movement range back up. And like I said, I'm going to scroll through this real slow. And you guys, go ahead and pause it if you need to catch up. Okay. That was a big one. That's out of the way. There's probably a typo or two in there I didn't catch. I hope you guys have good luck getting all that together too. Now, where does this all fit in? Like, we made color move nodes, and then we called that script. We made wipe move nodes, and then we called that script. Where are we going to do movement range? Well, the cursor, of course. So let's go to our cursor step event. Because really, the nodes, the map array, and the cursor drive this entire game. I mean, everything else is just sort of sitting around waiting for nodes and array or the cursor to tell them what to do. So, we're in our cursor step event. Right up in here, in our mouse check button pressed, MB left, right? When we first select them, we're going to give this actor 2 actions. So selected actor dot actions equals 2. And then we're going to do movement range. Hover node, that's where we're starting. I mean, we just clicked this node. Selected actor dot move. Selected actor dot actions. Although hover node, this is a bit oblique because we're clicking on them. So how about we do something a bit more complicated, but might read a bit better in the long run. So map selected actor dot grid X. Selected actor dot grid Y. There, we'll do that. Okay, I guess that might, well, you know what, never mind, that doesn't read better. To heck with it. You could do either. I'm going to go back to hover node. I think it's shorter and easier. I'm a mess today. I'm very sorry, folks. All right, so else, if we click on something and there's nobody there, we want to deselect them. But we also need to wipe nodes. Because let's say I clicked on Sandy and then I left-clicked somewhere else, it would deselect Sandy, but all those nodes would still be, they'd still all have all our movement range information in them. So every time we deselect an actor, we'd need to wipe the nodes. So, done. Now the right-click. So, all of this stuff we're going to keep. Eventually, when we right-click, our actors are going to move pixel by pixel, zoop, along a path to get to that node. For now, they're still going to click teleport. I think next video. Anyway, so we're going to keep all of this mess for now. Underneath this, we're going to do some stuff. If selected actor performed double move, deselect. Otherwise, decrement actions and reselect. Also, gosh, I just realized up here we have a mess. See this? Hover node.occupant equals no one and hover node.passable? We don't have to have that anymore. We're going to do and hover node.move node. So, if our hover node is a move node, we know that's already weeded out walls and it's already weeded out places where other characters are standing. So, that's fine by itself. So, now we're going to do the rest of our stuff. And I'm sorry I'm all over the place. I really am scatterbrained right now. But if selected actor performed double move, deselect. Otherwise, decrement actions and reselect. So, if hover node.g is greater than selected actor.move, then selected actor equals no one and wipe nodes. Let's scroll down a bit. Get ourselves space to work with. All right, else, so if they would have actions left over after this movement, then selected actor dot actions minus equals 1, and if selected actor dot actions are greater than 0, reperform movement range. I don't know why I put that comment there. Hover node selected actor dot move selected actor dot actions. And in this case, this is after we've moved, right? So we've moved, we've updated everything, but our hover node is hovering over where we've moved the actor to. So that's why we're passing hover node into movement range here. Else. So if our actions would be 0 after this movement, then selected actor equals no one, and we of course need to wipe nodes. All right, now of course down here, where if we right click on an invalid place, a place we can't move, where we deselect the actor, we also need to wipe nodes. Okay, finally. I know this has been a rough video, but we can green check out of all of this, and actually, give me just a second. That's not very nice. Here's the left and right clicks. That's what we changed. Go ahead and pause it. I'll give it a couple seconds, and you can go ahead and pause that if you need that too. Green check out of here and there. Okay, now I know this has been a rough video to code through and sit through, and normally it's smaller steps and then you get to run the game and test it and see progress, and this one has just been one gauntlet, a marathon. So, but finally, we can run the game. So, here goes nothing. Let's hope I didn't get any stupid errors. Alright, I'm going to left click Sandy. Why isn't it not liking neighbors? Line 33 of cursor. For movement range, line 33, abort. Okay, so movement range, line 33. You guys probably caught this. I don't understand. Oh, current dot neighbors. Gosh, I'm really sorry. So yeah, in here, in this while loop, this first for statement, we need to get the DS list size of our current dot neighbors. That's what we're accessing, the current node's neighbors. Can't believe I did that. That's a really stupid error. I'm very sorry about that, folks. Alright, so now I'm going to click Sandy. Boom, she has a movement range. I'm going to right click in a blue, so this is just one action's worth of movement. And there she is, and now she's also got her yellow up. She's ready to move again, over here. I'm going to click Danny. I'm going to move him straight to yellow. And it deselected. Now I'm going to click Sandy again, and I'm going to try to right click way over here. Wipes the nodes. Left click Sandy, left click over here. Wipes the nodes. Okay, so go ahead and move around a bit more, make sure everything's working out all right. If you've got an error, try rewinding and see where things went wrong. Next video, we're going to do some cool things. We're going to take all those parent variables we've been doing in all these nodes, and we're going to make a line showing how the character would move to get to the target node. And then we'll finally implement a path the character can move towards the node on. If you're enjoying the tutorial series so far, be sure to like, subscribe, or follow me on Twitter at SergeantIndy. Leave a comment below if you have anything to say. Thanks for watching, everybody. I'll see you next time.